Assalamualaikum and very good day to everyone. My name is NURBATRISYIA binti HALIN and my groupmate is SITI ZULAIKHA binti HAIZAM. Today we will be presenting our topic for discrete structure, which is mathematical induction. So without further ado, let's get started.
So first of all, what is exactly mathematical induction? So mathematical induction is method used to prove that a mathematical statement is true for all natural number. Think of it like we climbing a ladder. If you can step onto the first rung, and you know that whenever you one rung, you can always reach the next one, then you can climb the entire ladder no matter what, how tall it is.
That's a great analogy. And to carry out a proof by mathematical induction, it consists of two main steps. The first is the basis step, where we prove that the statement holds true for the initial value, usually when n equals to 1. The second is the induction step, where we assume the statement is already true for some value k, and then use that assumption to prove it must also be true for k plus 1.
Both steps must be satisfied. If we can show both of them hold, then the statement is proved that true for all numbers. Now let's look how this is formally structured.
Alright, here is the formal principle of mathematical induction. There are three steps involved in writing a complete proof. For the first step, we must prove P of n naughts. In other words, show the statement is true for the starting value, which we call n naughts. Second step, assume that P of k is true. This is our induction hypothesis, where we accept this as given for the purpose of the proof. And lastly, using that assumption, show that P of k plus 1 is also true. This is the key step. If we can always go from k to k plus 1, the domino effect takes over.
Once all three steps are done, we can state the conclusion P of n is true for all n greater than or equal to n. This is the foundation of every proof by mathematical induction. Now let's put this for practice with some example.
Now let's look at our first question. We will start with the basis step first. First, we let n equal to 1. So the left hand side is 1 and the right hand side is 1 squared equals to 1. Since both sides are equal, the statement is true for n equal to 1. Therefore, the basis step is proven. Now let's look at the induction step. For pk, we assume the statement is true for n equal to k. So this is how it looks like after we substitute the n to k. And again, we assume this statement is true. Now let's prove pk plus 1. This means we need to prove this statement is also true for n equals to k plus 1. So for this part, it will be the same. And then we just need to take 2k minus 1 and substitute the k into k plus 1. So it will be like this. So now it becomes 2k plus 1 minus 1. So for the right hand side, we just substitute the n squared into k plus 1 squared. Next, starting from the left hand side, we replace the first part using pk. So the expression becomes k squared plus 2k plus 1. Now we simplify it so it becomes k plus 1 squared. So the final answer is exactly the right hand side of pk plus 1. Therefore, pk plus 1 is proven. Since we have successfully completed both the basis and the induction step, the statement is true for all positive integers. Now let's move on to the second example. So this is the questions that we are going to prove. First, we perform the basis step by letting n equal to 1. Now substitute n equal to 1 into the right hand side. So on the left hand side, it becomes 1 square equal to 1. Since the right hand side and the left hand side both equal to 1, the statement is true when n equal to 1. This confirms that the formula works for the first positive integers.
For induction step, for the pk, it will be 1 square plus 2 square plus 3 square plus k square equal to k multiply with k plus 1 multiply with 2k plus 1 divided by 6. Then, for the pk plus 1, it will be 1 square plus 2 square plus 3 square plus k square plus k plus 1 square equal to k plus 1 multiply with k plus 1 plus 1 multiply with 2k plus 1 and plus 1 divided by 6. And then, starting with the left hand side, for induction step, using our assumption for the pk, it will be k multiply with k plus 1 multiply with 2k plus 1 divided by 6 plus k plus 1 squared. Next, we simplify the expression by writing both terms with the same denominator and factorize the common factor of k plus 1. After simplify, we can obtain that k plus 1 multiply with k plus 2 multiply with 2k plus 3 divided by 6. This is exactly the right hand side of the pk plus 1. Therefore, pk plus 1 is true. Since the basis step and induction step have both been proven, the statement is true for the all positive integer. This is exactly the right hand side of example 3. Our question is 1 cube plus 2 cube plus 3 cube plus n cube equal to n multiply with n plus 1 divided with 2 and square. For the basis step, when n equal to 1, so n multiply with n plus 1 divided by 2 and square, n will be substitute with 1, so it will be 1 multiply with 1 plus 1 divided by 2 and square. After that, when 1 plus 1 is 2, 2 divided by 2 is 1, and 1 square will be 1. So it's true that P1 is true. Next, we move to the... Okay, so for induction step, we assume that statement is true for n equal to k. For the pk, 1 cube plus 2 cube plus 3 cube plus k cube equal to k multiply k plus 1 divided by 2 and power of 2. For pk plus 1, that means 1 cube plus 2 cube plus 3 cube plus k cube plus k plus 1 cube equal to k plus 1 multiplied with k plus 1 divided by 2 and power of 2 plus 1 multiplied with k plus 1 divided by 2 and power of 2. So it will be k plus 1 multiplied with k plus 2 divided by 2 and power of 2. When we substitute with pk, it will be k. When we substitute with pk, it will be k multiplied with k plus 1 divided by 2 power of 2 plus k plus 1 cube. Then, we simplify, we factorize the common factor k plus 1 square and finally obtain.
And with that, we have reached the end of our presentation. To summarize what we covered today, mathematical induction is a powerful technique in discrete mathematics for proving statements that hold for all natural numbers. It relies on two key steps: the basis step to get us started, and the induction step to carry the truth forward one step at a time.
We demonstrate with the truth of 3 examples, proving formula for the sum of odd numbers, the sum of square, and sum of cubes, all using the same elegant two-step structure.
We hope this presentation has made mathematical induction clearer and easier to understand. Thank you so much for your attention.
If there is any question, we would happy to answer them. Thank you for everyone.